Welcome back to class 19, and we're continuing on with more examples for the inequality of Clausius. I'm not sure this has anything to do with the inequality of Clausius. I think it has to do with other examples we want to cover in this chapter, because this is the last class of that chapter 5. So you go, if an air conditioner on a hot summer day removes 8 kilowatts of energy from a house that's at 21 degrees Celsius, and pushes the energy to the outside, which is 31 degrees Celsius. I should learn this in Fahrenheit because I have no idea what those are in American units. The house has a mass of 15,000 kilograms and an average specific heat of 0.95 kilojoules per kilogram degree Kelvin, which is really sort of like treating it like a solid, I guess you would say. In order to do this, I should say the specific heat. I would call that the heat transfer coefficient, maybe. Yeah, I think you could say that. Yeah. Anyway, in order to do this, the cold side of the air conditioner is 5 degrees Celsius. Okay, so what they're saying is you can't just get down to 21 degrees Celsius. You need to have the cold side of the air conditioner be colder than the 21 degrees Celsius. And then the hot side of the air conditioner is 40 degrees Celsius, which also makes sense because you can't just go to 31 degrees Celsius. You need to have a heat exchanger that's blowing hot air into the, even though the outdoors is hot, the air conditioning's exhaust needs to be higher. The air conditioner has a coefficient of performance that is 60% of the corresponding Carnot refrigerator. Find the actual coefficient of performance of the air conditioner and the power required to run it. So I should say right away that I noticed, but you might not, that there's distractors right here. This guy and this guy are not necessary, and we may even find that this 31 degrees and 21 degrees, no, that's not actually necessary right now, I think. And I'm looking at the thing right now. I don't think we actually need that. I think what we really need is the 5 and the 40, right? That's actually what we need. So that's but distractors, got to be careful. You got to make a decision which temperature sets that you're going to need to use for this problem. I'm 99% confident because I probably looked at the solution manual. Okay, so the what we're moving, they tell us what we're moving. We're expelling 8 kilowatts of heat out of this thing, which, by the way, I drew a little house, so I'm going to draw a little house. So we have the T, the inside temperature, inside is going to be equal to 21 degrees Celsius, but we have a, we need a low temperature side of the refrigerator to be 5 degrees Celsius in order to make the house 21 degrees. And then the same thing for the outside temperature. It's going to be 31 degrees Celsius. And then so the the heat rejection is 40 degrees right here. So that's going to be on the thing right there. And we do know that the coefficient of performance of the refrigerator is 60% times the coefficient of performance of the refrigerator if it were a Carnot refrigerator. This is supposed to be a P. Not doing so great with the P. Okay, so here's like the house, just to give me like a little bit of thought process. And here is the, I was going to get the names confused until I think about it a little bit more, but I think we're going to call that the evaporator. And down over here is the condenser. Is that true? Yeah, I think so. And then there's a, okay. Oh, you can't see it. Yeah, sometimes I just I get my head right. I can't remember things like that. Anyway, so basically, if this thing's expelling heat out, this Q dot out, and that's what we want to color here yeah, that's the QL. So we're we're taking this out. If this thing is in equilibrium, the same amount of heat is leaking in. So I like to call that the leak. It's like it's leaking in, and then we're putting it out, and that should be, so this is going to be the out. And so it's actually, going to say the same thing right in there. It's coming in, into the house, coming into here, coming out of there. This is the TH is on the coils, whereas this is the T outside. And then on the coils right here, the TL is right there, whereas this is the T inside. So heat is moving from here into the house, coming into this side, and then coming out. So this is the low, the QL coming into here, and then we're putting. I should point out that this is not. Yeah, this is the same thing as this, but this is not the same thing as this because we're putting work in right there. Bob is coming in right there into the compressor. Okay. My bad if I said that wrong at any point. My bad. So let's see. Let's look at the Carnot. The COP ranking of the Carnot, which is going to be 1 minus TL over TH. No, that's an engine. My bad. Got to be careful. For refrigerator, I hope I didn't do this wrong somewhere else. TL over TH minus TL, all right, on the temperature scale. And we go 5 plus 273. That is the low temperature that we're coming to. And then the high temperature, and we don't need to do the 273 for this. But we can. So you can say 40 plus 273 minus 5 plus 273. But the 273 is kind of not important right here on the bottom. And so our coefficient of performance, looks to be R, tired. R, Carnot, is going to be equal to 7.943. Okay, so the real one, we are told, is 60% of that. 7.943, which is now going to be equal to 4.766, which is one of the answers, so I'm going to box it right there. I said the actual, and then how much power. Well, remember that coefficient of performance, we need to get this up here, of a refrigerator is going to be QL, the amount of heat extracted, divided by the power. So we can find the power by dividing the QL, which is 8 kilowatts, by our 4.766. So our required power is going to be 1.679 kilowatts. And then on the next question, the air conditioner is in the previous problem is turned off. How quickly does the house heat up in degrees per second? I like this because it has like some kind of like, you can maybe picture how much that's going to, what that's going to be like. Well, this is a heat transfer type of problem. So we could say, well, a heat transfer is usually the flow rate of heat. Is going to be equal to the mass flow rate of whatever is moving along, usually a fluid, but in this case, it's going to be a solid. So we're going to see what we're going to do that in a second. And that's going to be times delta T. But this is not a flow problem. This is not a fluid flow problem. This is a stationary house. And now we're going to do time rate. So what is the heat flow rate going to be? Of course, you know what we're saying, by the way, once again, I drew the house because here's heat leaking in, and then here's Q dot L coming into there, right? So this must be equal to that on a regular day, right? So now we're going to say, well, how fast is this thing going to heat up? We can go, here's our CP, and I kind of figure this as being a solid. And now instead of this being a mass flow rate, it's just a given mass, it's going to be our temperature change, right? And that's even just to change out to change out the units. So this is dt right here. And that's kind of what we're looking for, right? We're looking for the rate at which the temperature changes. Like how quickly does the temperature change? So we write dt is going to be, here's the house, the leak. We'll say that heat is leaking into this, leaking into the house, divided by the mass of the house, and the, I'm saying specific heat, but it's like the heat transfer coefficient, really, of this thing. So we have, this is 8, and that's kilowatts, which could be kilojoules per second, right? And here is 15,000 kilograms. And this thing is 0.95, and what did they say it was? Kilojoules, 0.95 kilojoules per kilogram degree Kelvin, right? So the kilograms go away right there, kilojoules go away, and you get degrees Kelvin per second. So I'm going to write this over here to get a little more space underneath. And what you're left with is a very, very small number, but I'm going to change it to something more digestible here in a second. Minus 4, and these are degrees Kelvin per second. But you could just go ahead and multiply by 3,600 seconds per hour, and then also degrees Celsius per degree Kelvin. They're identical, really, in terms of the ratio of them. And so we get dt, the change in temperature with time is going to be 2.02 degrees Celsius per hour. And you can actually think, and I couldn't give an idea what the, this I can't get my head wrapped around this, but I could figure out that the house is going to get 2 degrees warmer per hour when the air conditioner is turned off. One big problem with that is this heat rate of the leak won't remain constant, because that heat rate is based on the temperature difference between the outside and the inside. And once the inside temperature gets higher, then the heat rate changes. So this is sort of like an instantaneous heat rate, but we can kind of use it for the near term as an approximation for how quickly the house will get warmer. Anyway, I like this problem because it's something I can wrap my head around, and that's makes it better for me. I can actually appreciate the usefulness of having to calculate something like this. We'll see you in the next example.